Welcome to my presentation. I am going to make a brief introduction about planar magnetics for power converters. Magnetic components often come with significant trade-offs: size, power loss, cost, and complexity. They dominate not just the volume and weight of converters, but also the thermal performance and efficiency. Now, while traditional magnetic designs have come a long way over the years, today's demands for higher efficiency, smaller size, and easier manufacturing are pushing us to rethink how we approach magnetics. That's where planar magnetics, especially PCB-based designs, they've become a major trend in modern switch-mode power supplies. Traditional magnetic components are typically bulky and operate at relatively low frequencies. However, with the emergence of wide bandgap semiconductors like gallium nitride and silicon carbide, switching frequencies have increased significantly, driving the need for more compact magnetic designs. Conventional wire-wound magnetics have a difficulty to meet these high-frequency demands, making PCB-based magnetics a promising solution for high-efficiency and high-density power applications. One of our key research subtopics on planar magnetics is the winding resistance modeling at high frequency. At DC, or really low frequencies, it's straightforward. The resistance is just RDC, which we get from equation 1.1, resistivity times conductor's length divided by the cross-sectional area. But at high frequency, things are changed. Since only that thin outer layer, the skin depth, is carrying most of the current, as you can see in figures 1.4 and 1.5, the effective cross-sectional area gets smaller. And when the area shrinks, the resistance goes up. That's why the AC resistance is higher than the DC resistance. It's like trying to push the same amount of current through a narrower pipe. Next up, we've got the proximity effect for high-frequency winding resistance modeling. While the skin effect comes from the conductor's own magnetic field, the proximity effect happens because of the magnetic fields from neighboring conductors. Those neighboring fields distort how the current flows inside your conductor, pushing it even more towards certain areas of the surface. In other words, proximity effect basically gives the skin effect a little extra shove, forcing the current into an even smaller region. And just like with skin effect, when the effective area for current gets smaller, your AC resistance goes up. This gets especially bad when you pack a lot of winding layers tightly together, exactly what the finite element simulation in figure 1.7 shows. The stronger color means higher current density in the conductors. Another consideration which often gets overlooked in planar magnetics design is the radius effect. Because the conductor width is much larger than its thickness, the inner edge of the winding ends up having lower impedance than the outer edge. That means more current tends to flow along the inner edge of the conductor. This uneven current distribution is what we refer to as the radius effect, and it could have a noticeable impact on AC resistance and leakage inductance. When we design inductors or LLC transformers, air gaps are often needed. The traditional 1D solution, Dowell's analysis, doesn't really hold up anymore. That's because it doesn't take the fringing effect from the air gap into account. According to Dowell's assumptions, the current tends to move toward the surface of the conductors because most of the leakage flux runs parallel to the conductor surface. But when there's an air gap, things change. The fringing flux around that gap causes the current to behave differently. It actually starts bunching up more along the edges of the conductors. This is the current trying to cancel out the local fringing field. Here we quantify how serious this fringing effect can be. We are comparing the AC resistance with and without a 0.5 mm air gap. At 1 MHz, RAC jumps from 13.5 to 337.4 milliohms. That's about 25 times higher. So just having a small air gap can drastically increase the AC resistance due to intensified fringing. This clearly shows that if we are targeting high efficiency performance, fringing needs to be carefully controlled. Our research also relates to a subtopic in planar transformer winding loss, parallel windings. When we deal with high current applications, we often use multiple windings in parallel. We normally don't parallel the conductors directly because the eddy current effect, nearly no current running in the middle layers. So it is a waste of copper materials. What we do is to interleaved windings. We've got 3 classic cases here, all using a 4:1 turn ratio. That means the primary has 4 turns in series and the secondary has 4 layers in parallel. However, different winding layout can bring significant differences in winding loss. In case 1 and case 2, you'll notice the current density isn't evenly distributed. This imbalance causes what we call circulating currents, which lead to extra losses. Case 3, on the other hand, shows a more balanced current distribution across the parallel windings. But there's a trade-off. The current is sharply concentrated at the conductor surfaces, which indicates a strong eddy current effect. So, at higher frequencies, where eddy currents dominate, case 3 will actually have higher AC resistance. So even though parallel windings seem like a good idea for high current, they require careful design and modeling to avoid unexpected losses. Another subtopic in planar magnetics is how to model the leakage inductance. Here I would like to highlight a common misconception that planar transformers intrinsically have low leakage inductance. That's not really true. In fact, planar structures can actually have higher leakage compared to traditional vertical windings. That's because planar designs typically have a longer mean turn length, which contributes to more leakage inductance. To illustrate this, we've run a simulation comparing a conventional vertical structure with a planar structure, keeping everything else the same. Same core geometry, same number of turns, same winding width and thickness, and so on. The results show that the planar structure has about twice the leakage inductance of the conventional one. However, planar designs do have a big advantage. They make it much easier to interleave windings, especially when using PCB layouts. When we place primary and secondary windings in alternating layers, we improve magnetic coupling and significantly reduce leakage inductance. Winding capacitance is an important yet often overlooked aspect of power magnetics. Different winding layouts can lead to substantial variations in the resulting capacitance. In our research, we investigate how winding capacitance can be modeled for various winding schemes, and we explore strategies to mitigate these parasitic effects. Understanding the equivalent capacitance and total electric field energy is crucial for optimizing transformer efficiency and functionality. Interleaved winding is a key advantage of planar PCB magnetics. Because multiple copper layers are readily available in a PCB, it becomes much easier to implement interleaving between primary and secondary windings. This layout reduces AC resistance and lowers leakage inductance, leading to improved overall magnetic performance. The slides presented above provide a brief overview of our research topics in this regard. If you are interested in learning more, we invite you to explore our publications and follow our ongoing research developments. We will continue to update and share our latest results as our work progresses.